Welcome to QHSE Talks, the podcast where safety meets leadership, and where we go beyond checklists and compliance to explore the systems that keep high-risk industries running safely, efficiently, and intelligently. Today, we're stepping into the operational heart of oil and gas safety, Element 2 of the NEBOSH International Certificate Hydrocarbon Process Safety 1. This element isn't just another chapter in a textbook. It's the living framework that defines how risk is controlled, how work is authorized, and how people, processes, and equipment come together to keep danger at bay. Because in this industry, safety doesn't happen by chance. It's engineered, managed, and constantly reinforced. From the way we select and supervise contractors to how we manage process changes, shift handovers, and permits to work, every procedure represents a barrier between normal operations and potential catastrophe. Element 2 brings those barriers to life. It's about ensuring that the right person with the right knowledge performs the right task under the right conditions. It's about building resilience into every layer of operation, from asset integrity and maintenance to isolation systems, gas freeing, and ignition control. And the deeper you look, the clearer it becomes. Every control is part of a chain, and if one link fails, the whole system can unravel. That's why this element isn't theoretical, it's practical, procedural, and relentless in its demand for precision. So in this episode, we're going to unpack what those systems look like in real life. We'll examine the structured approach behind contractor management, the discipline of safe shift handovers, and the importance of formalized systems like permits to work and management of change. Because the difference between a safe operation and a catastrophic one often comes down to the strength of these very processes. And where does it all begin? It starts with the people who might not wear your company's logo, but whose actions can define your company's safety record.
Right, contractors. The reliance on them in this industry is simply staggering, isn't it? When you talk about thousands of workers who aren't permanent employees suddenly operating in these high-hazard environments, why are they so central to the whole oil and gas machine?
Well, they are central because the sheer scale and specialization of the work demand it. It's almost unavoidable sometimes.
Okay.
Contractors are used for practically everything. Massive construction and installation projects, highly specialized repairs, maintenance tasks, demolition, deconstruction, running support vessels, providing complex diving services,
Wow.
and even operating sophisticated drilling or exploration rigs. They offer specialized skills and, crucially, workforce flexibility that core organizations simply can't maintain in-house efficiently.
Okay, that makes sense. But every time a new contractor comes on site, they introduce an unknown quantity, right? A varying level of competence, maybe less familiarity with that specific site's unique rules and hazards.
Exactly.
This is where the shared responsibility principle kicks in.
Yeah.
Correct? The plant owner can't just sign a contract and wash their hands of it.
Absolutely not. Correct. The responsibility for site safety remains firmly with the organization operating the plant.
Huh.
You simply cannot outsource the risk. That's fundamental. So the 5-step contractor management approach we're discussing, it's a systematic defense mechanism. It's designed to ensure that external competence is properly vetted and integrated safely before they even start work. It's about active risk management, not just passive delegation.
Okay, let's detail those 5 steps then, starting with step 1. Planning. This sounds like the foundational agreement stage. What happens here?
Planning is absolutely the definition phase. It begins with the organization clearly defining the job's scope and its boundaries. What exactly needs to be done?
Nail it down.
Precisely. Then comes the mandatory hazard identification and a rigorous risk assessment specific to that work. You have to ask, what inherent hazards will this contractor encounter on our site? And importantly, what new risks will their presence or their actions introduce?
Right, because they bring their own risks too.
They do. And based on that assessment, the organization must specify every mandatory health and safety condition they require. And this isn't just, a generic list of rules. These are specific, non-negotiable requirements tied directly to the assessed risk.
And I see here a crucial part of this step is dialogue. It's not just issuing instructions.
Absolutely vital. Critically, these initial planning conditions must be discussed with the potential contractor before selection. You need to have that conversation up front.
Why before?
Well, it ensures that the contractor fully understands the magnitude of the task and, crucially, the expected safety controls.
Mhm.
If they look at the requirements and say, we can't meet that, or that's too onerous, well, then they won't even be considered. It filters them out early.
Okay, that makes sense. That transparency then naturally filters into step 2, choosing a contractor. The focus here is vetting competence over just picking the lowest bid, I assume.
Competence over cost, always, when safety is paramount. This is the main vetting stage. First, the organization must precisely determine the required technical and safety competence for the task. For instance, are they certified for working at height? Do they have a proven track record handling high-pressure systems safely? Specifics matter.
So how do you check? What mechanisms are used to actually determine if they are competent technically and safely?
It's a rigorous process, or it should be, multifaceted. It involves using detailed questionnaires, demanding concrete evidence, things like training records, formal qualifications, maybe industry certifications, and crucially, reviewing their past safety track record.
How do you review that? References.
References, yes, but also looking at their incident statistics, if available. What's their history? And you need to see their proposed safety method statement for the specific job.
Right, the method statement. So it's not enough for them to say they're safe. They have to prove it in writing for this specific task. What is that statement exactly?
Think of it as their contract of safety for this job. It outlines, step by step, how they plan to execute the task. Could be complex, could be hazardous from mobilization right through to cleanup, and it details exactly which safety precautions will be used at each stage.
So if that method statement is weak, or maybe it ignores critical site hazards, exist.
Then they're out. Immediately disqualified. It shows they haven't understood the risk or aren't prepared to control it adequately.
Right. And what if that contractor plans to use its own subcontractors? That happens all the time, doesn't it?
Very common. And that decision has to be addressed right here in step 2. First question. Is subcontracting even permitted for this particular high-risk task? Sometimes the answer is just no.
Okay.
But if it is permitted, the primary contractor must demonstrate they have robust systems in place to vet and manage safety competence all the way down the chain, to the third parties, the fourth parties, everyone involved.
So the main organization needs to ensure that safety integrity doesn't get diluted further down the line.
Precisely. The responsibility flows down, but the oversight has to remain strong.
Okay, so once selected, vetted, method statement approved, we move to the operational phase. Step 3, contractors working on site-controlled entry and induction. This sounds like setting up the immediate controls right there in the field.
It is. It's about establishing immediate control and accountability on the ground. First, every contractor, every single person must adhere to mandatory sign-in and sign-out procedures.
Why is this so critical? Headcount.
Headcount, yes, but it's absolutely critical for emergency management. Knowing who is on site, where they're supposed to be working, and confirming they've left safely, you need that visibility.
Got it.
Then, a singular site or installation contact person must be named. This provides a clear point of communication, a go-to person for the contractor, and establishes that line of authority.
And induction isn't just a formality.
No, it's crucial. Before any tools are picked up, the organization must reinforce site-specific rules, health and safety information, emergency procedures, and review any changes that might have happened since the initial planning phase. Conditions change.
So after they've had their induction, what's the final hurdle before they are actually granted permission to, swing a hammer or turn a wrench?
The final job check. This is often a field supervisor walking the job site with the contractor's supervisor. They're verifying that the physical conditions on site match exactly what was agreed upon in the permit and the method statement.
Ah, okay. A final check that reality matches the plan.
Exactly. Only when that check is satisfactory is permission formally granted to start the work.
Right. Then step 4 is where sustained diligence is required. Keeping a check. You can't just set them up and walk away, trusting the paperwork. You have to verify the execution.
Continuous monitoring is essential. You can't just assume everything's going according to plan. The necessary degree of contact and oversight, well, it has to be calculated based on the job's duration and complexity.
Give me an example.
Sure. A short, relatively low-risk job might only need, say, weekly checks. But a critical welding job happening right next to live pipework, that might need constant direct supervision. The level of oversight matches the level of risk.
And what are you checking for during these checks?
You're checking compliance. Are they following the agreed safe working procedures outlined in their method statement? Are they using the right PPE? Are the barriers still in place? You're actively verifying.
And what if things change mid-job? Say the plan needs adjusting, or maybe their main supervisor quits unexpectedly.
That triggers an immediate evaluation. Any significant incidents, even near misses, or important personnel changes like the loss of a key safety supervisor must prompt the organization to reevaluate the impact.
So you might need to adapt your monitoring strategy.
Immediately. You might have to pause the work altogether or assign a new, maybe higher level of direct oversight from your own team. You have to react to changes.
Okay. Finally, step 5. Reviewing the work. How does this close the loop? How does it help continuous improvement across the whole organization?
This is the learning stage, the data collection. The job isn't really done when the final invoice is paid. It's done when the review is complete.
So you review the quality of the work itself.
Yes, you review the quality, of course, but perhaps more importantly, from a safety perspective, you review the contractor's overall safety performance standard throughout the job. Were they compliant? Did they meet their method statement obligations? Were there any issues?
And what do you do with that information?
The lessons learned are formally recorded, both positive performance, maybe they had a great safety initiative, and negative performance data. This information then directly feeds back into the system. It informs the planning and selection criteria for all future contractors, strengthening the entire vetting process moving forward. It's about getting smarter each time.
That 5-step system seems like a really robust framework for managing external personnel. But the next section deals with managing the inherent hazard of the tasks themselves, whether done by contractors or in-house teams. Let's shift to section 2, controlling operations permit to work and isolation.
Right. And here's where we get to arguably the core procedural safety mechanism on any high hazard site, the permit to work or PTW system.
PTW, I hear this term a lot.
It is arguably the single most vital formal mechanism for controlling non-routine hazardous work. It's that piece of paper, yes, but it's the documented process that translates the risk assessment into explicit, time-bound, actionable instructions for a specific task.
Okay, it might seem like just a mountain of paperwork to some, but you're suggesting it's much more profound, almost like a physical barrier against disaster itself.
In a procedural sense, yes. Think of the PTW as a formal, temporary contract for safety for that specific job. Its purpose is threefold. Ensure risks are actively identified, assessed, and controlled before the task even starts.
Okay.
Ensure those controls are maintained throughout the duration of the work. And, crucially, ensure the plant or equipment is safely checked and recommissioned at completion. If a high-hazard task doesn't have a valid, correctly completed PTW, it simply cannot proceed. Full stop.
Okay, let's break down the critical elements of this permit document then. It sounds like it needs to be exhaustive.
It has to be comprehensive, yes. First, clear identification. The title of the permit, a unique permit number, and critically, a reference to all related isolation certificates. This links the procedural safety document immediately to the physical safety barrier, the isolation.
So it connects the paperwork to the locks on the valves.
Precisely. It must specify the precise equipment involved, the exact location down to the specific tag number, and the detailed nature of the work to be carried out. No ambiguity allowed.
Right, and then the core safety content, what's listed there?
It must list all the identified hazards associated with that task and location. Then, critically, the necessary precautions required to control those hazards and the specific personal protective equipment, PPE, needed.
Okay.
On the administrative side, it dictates the required authorizations, who needs to sign off on this permit before work can start. Usually multiple people, operations, maintenance, safety.
Makes sense.
It specifies the exact date, the start time, and very importantly, the defined duration for which the permit is valid. Permits expire.
What about accountability for the people doing the work?
Huge part. The permit demands formal acceptance, usually a signature, from those performing the work. By signing, they are acknowledging they understand the hazards, they understand and accept the precautions, and they commit to adhering to the specified safety procedures.
It's a personal commitment.
It is. And finally, upon completion of the work, there's the certification process. This involves checks and sign-offs confirming the work is finished, the area is safe, any testing has been done, and the plant is ready to be safely returned to service. This cancellation or handback section is vital and sometimes overlooked.
Okay, so what types of work automatically trigger this complex PTW requirement? It's not for every single task, presumably.
No, it's typically for non-routine work or any activity that introduces a significant immediate risk. The classic examples include hot work, anything generating heat, sparks, or flame, like welding, grinding, cutting, burning.
Okay, obvious fire risk.
Absolutely. Then any work on live or high voltage electrical systems. Also, Working at height or working over water, these carry unique fall and rescue risks. And any work within confined spaces due to potential atmospheric hazards, engulfment risks, or difficult access.
So basically any maintenance or non-standard operation that deviates from normal safe routine.
That's a good way to put it. If it's not routine and it carries inherent hazards, it almost certainly needs a PTW.
Okay. The PTW defines the risks and the procedural precautions. But the physical control, the ultimate hard barrier against harm, is safe isolation, which involves the lockout, tagout, or LATO procedure.
Exactly. LATO is the fundamental physical barrier against the accidental re-energization or release of energy. Safe isolation means interrupting, disconnecting, and physically separating all potential motive power or energy sources from the equipment being worked on.
Right.
And then securing that disconnection with lockable means padlocks, chains, blanks, so it cannot be accidentally or inadvertently reversed while people are potentially in harm's way. You must prevent the equipment from moving, spinning, heating up, or pressurizing unexpectedly.
Now, in a complex processing environment, people often think mainly of electrical power when they hear isolation. But you're saying there are many other stored and residual energy sources that pose a threat.
That's a critical point and a common oversight. The safe isolation procedure must cover all potential energy sources. Yes, electrical supplies are key, but also things like hydraulic oil power systems, pneumatic power, which uses compressed air or gas, and any stored compressed energy within those systems. Residual energy remaining in systems even after they're switched off, think about tension and springs, the potential energy of a raised weight due to gravity or trapped pressure.
Right, things that can still move or release.
Exactly. Also, combustion engines need isolation. And high-pressure systems like steam lines or high-pressure water systems. If any relevant energy source is missed during the isolation process, the LATO is incomplete and the worker is potentially at severe risk.
Okay, let's detail the actual isolation procedure then. Say a maintenance worker needs to enter a piece of equipment, like a vessel. What is the sequence they or the operations team must follow to make it safe?
It's typically a methodical, step-by-step sequence designed to eliminate danger systematically. First, the machinery or plant section must be stopped using its normal operational controls, the stop button, basically.
Standard shutdown.
Yes. Second, and this is absolutely crucial and often missed, all residual or stored energy reserves must be safely exhausted, dissipated, or discharged. Think about bleeding pressure from a vessel, draining a hydraulic accumulator, or releasing tension in a spring mechanism. That stored energy must be gone.
Got it. Drain it down.
Third, all moving parts must be secured in a safe position. Chalked, pinned, blocked, whatever it takes to ensure there's no chance of accidental movement, like something heavy falling or rotating.
Okay, then comes the actual physical break.
Yes. Fourth step. The electrical main isolator, or isolators, if there are multiple feeds, must be physically turned to the off position.
Flick.
Fifth, a padlock must be fitted to that isolator switch handle, securing it in the off position. This lock should be uniquely identifiable, maybe labeled or coded, showing who applied it and why linked to the specific PTW.
And what if multiple people or teams need to work on it? One lock isn't enough then.
Correct. In that case, you use a safety clamp or hasp. It's a device that fits over the isolation point and it has multiple holes. Each worker or team representative working under that isolation applies their own personal padlock to the hasp. The equipment cannot be re-energized until every single lock is removed.
Ah, so everyone's protected by their own lock. That's the lockout part.
Exactly. And the sixth step is the tag out. You must post an appropriate warning notice, a tag, right there on the machine's normal starting mechanism, and also on the main isolator itself where the locks are.
What does the tag say?
The tag clearly communicates, danger, do not operate, identifies the equipment, states why it's isolated, e.g. maintenance in progress, usually references the PTW number, and indicates who performed the isolation or who holds the keys. It warns everyone, operations, other maintenance crews, management, that the equipment is intentionally shut down for safety reasons and must not be touched.
So the lock provides the physical security and the tag provides the clear communication.
Precisely. ALOTO, lockout, tag out, both are essential.
Okay, so if the PTW and LTO are about controlling the known hazards of specific tasks and equipment, the next section, Section 3, addresses a more systemic vulnerability, mitigating human error, especially during critical transitions like handover and management of change.
Yes, human factors are arguably the biggest challenge. Studies consistently show human error is a primary or contributing factor in the vast majority of major industrial incidents. And the handover process, particularly a shift change, is a well-known weak link. It's often described as a safety-critical communication for a reason.
Why is it so risky? You're just telling the next crew what happened.
Well, think about it. You are transferring complex, dynamic, real-time knowledge about the state of a potentially hazardous plant between different groups of people. They might be tired at the end of their shift. The incoming crew might be just waking up. There might be time pressure, or maybe there's friction between the shifts.
Okay, I see. So what are the common dangerous pitfalls that can degrade safety during this handover transition?
The problems typically stem from failures in communication structure and accountability gaps. Common issues include, well, simply not allocating sufficient time for a proper handover. Everyone's rushing.
Yeah.
Often there's a failure to hold or even attend formal shift handover meetings. People rely on informal chats in the corridor or just reading the logbook, which might be incomplete. We also see conflict sometimes. The outgoing shift might deliberately dump unwanted, difficult, or hazardous tasks onto the incoming team without providing the full necessary context.
That sounds dangerous. And how does this poor communication affect the formal safety systems we just discussed, like PTWs?
That's a critical link. Poor handover practices often lead to poor shift record keeping, or worse, a failure to properly communicate the exact status of open, suspended, or recently cleared permits to work and their associated isolations.
So the incoming shift might not know a permit is still live or that an isolation is still in place.
Exactly. It creates a dangerous lack of continuity. The incoming shift might wrongly assume a piece of equipment is safe to operate when it's actually under maintenance lockout. Or they might assume a permit they find is still valid when it actually expired an hour ago. Huge potential for error.
If these communication gaps are the core problem, what are the key principles for making handovers effective and safe?
The organization has to recognize handover as a high-priority, safety-critical function, not just an administrative task. It must be conducted face-to-face whenever possible, ideally in a designated quiet area free from distractions. And critically, it must be explicitly two-way.
What do you mean by two-way?
The outgoing shift isn't just delivering a monologue or reading from a log. The incoming shift has a responsibility to actively listen, to ask clarifying questions, and to confirm their understanding of the plant status and ongoing risks. Both parties must share responsibility for the successful transfer of information.
Okay, active listening and question.
Yes. And while verbal communication is key for nuance, the process must rely heavily on standardized written documentation and records, clear logs, checklists, PTW status boards. This ensures continuity and provides a reliable reference, especially during complex operations or if someone was absent.
Are there specific techniques or systemic solutions used by high reliability organizations to structure these handovers, even when people are tired or rushed?
Yes, definitely. Many organizations mandate formalized communication protocols to add structure. A popular one is using something like the SBA technique situation, background, assessment, recommendation. Yeah, it provides a clear, concise structure for conveying critical information. What's the current situation? What's the relevant background? What's my assessment of the situation? And what's my recommendation or what needs monitoring? It helps prevent long, rambling narratives that might miss the crucial details.
So it standardizes the information transfer.
Exactly. And having dedicated, non-distracting handover rooms or periods also helps ensure the focus remains purely on that safety-critical data transfer.
Okay, that makes sense for shift changes. Now, let's talk about management of change, or mooshing. If handover is about people transitioning smoothly, moosh seems to be about protecting the plant's physical and procedural integrity during transitions or modifications.
That's a great way to put it. MOSHOC is the formal system designed to prevent safety drift, that slow, often unnoticed erosion of safety standards that can happen when you accumulate lots of small, seemingly insignificant changes over time.
Right, the death by 1,000 cuts scenario for safety.
Precisely. Therefore, formal, written MOSHOC procedures must be in place, and they must ensure that all proposed changes, whether they're temporary or permanent, whether they affect process systems, equipment, operating procedures, or even staffing levels, are rigorously assessed for their potential impact on safe operation before they are implemented.
Before. That's the key word.
Absolutely. It's mandatory because one small alteration, made with good intentions perhaps, can have massive, unforeseen, and potentially catastrophic consequences across the entire interconnected system.
So, to prevent those unintended consequences, what sort of documentation needs to be consulted during an ADSHA review? You really need to understand the plant's history and its original design intent, right?
Absolutely. The mouth key evaluation requires quite extensive documentation review. You must consult the original design documents and philosophy to understand the plant's baseline safety case. You need up-to-date process flow diagrams, PFDs, and piping and instrumentation diagrams, P&IT.
PFDs, okay.
Critically, you must check things like cause and effect diagrams. These show how a change in one area might impact automated safety functions or interlocks elsewhere. You also need to review the current list of control system settings, alarm set points, and emergency trip parameters.
Why check those specifically?
Because a proposed change might inadvertently alter a pressure that affects a trip setting or bypass a safety function that the original design relied upon. You also need equipment specifications and hazardous area classification drawings. Ignoring any of these means you risk introducing a weakness or hazard that the original design carefully mitigated.
So the change proposal itself needs to be thoroughly documented and scrutinized. What needs to be in that proposal?
It needs to be robust. The documentation must clearly detail the reason for the change, the proposed date or duration, and its expected lifetime, temporary or permanent. Crucially, it must comprehensively detail all potential associated health, safety, environmental, and operational impacts, positive and negative.
Okay.
It must clearly identify the authorized personnel required to review and approve the change. This often requires multidisciplinary sign-off from operations, engineering, maintenance, safety, maybe even environmental specialists, depending on the change.
So it forces different perspectives to look at it.
Yes, prevents siloed thinking. And what about that natural human tendency, especially under pressure, to maybe bypass the complex MUSI system? You know, it's just a small tweak, let's just do it quickly. What's the defense against? That's a constant battle. The final, crucial element baked into a good MUSI system is the provision for monitoring and auditing. The system must actively monitor the implementation phase. By having checks to ensure that procedures are not short-circuited, that nobody starts the physical work before the formal approval is granted, or verifying that the final modification is installed exactly as approved, not with some field improvisation. There must also be a clear path for communication and feedback, even if a change proposal is rejected, so that the person who proposed it understands why the system needs to remain in its current configuration for safety reasons.
Right. Closing that loop is important too. Okay, we've established this strong procedural safety framework managing contractors, PTW, LRO, handover, MOSI. But if the physical plant itself, the hardware, is unsound, then no amount of paperwork is going to save the day, is it?
Absolutely not. The procedures manage the activity, but the equipment has to be fit for purpose. This brings us perfectly to Section 4, maintaining the plant asset integrity and maintenance strategy.
Asset integrity. What does that term actually mean in this context?
Asset integrity is fundamentally the ability of an asset, a pipe, a pump, a vessel, the whole installation, to carry out its intended function effectively and efficiently over its entire planned life cycle, while always safeguarding personnel, the environment, and the asset itself. It's about maintaining fitness for service.
And this is managed through specific systems.
Yes, typically through what's called an Asset Integrity Management System, or AIMS. It's the overarching framework of procedures, practices, and resources to ensure integrity.
You mentioned the entire planned life cycle. Integrity isn't something achieved once at the start. It's a commitment that spans potentially decades, right? What are the critical stages of this asset life cycle that AIMS needs to address?
That's right, it's cradle to grave. There are generally considered to be 6 key stages. Stage 1 is design. This is where engineers aim for the optimal technical and safe solution, considering material selection, corrosion allowances, redundancy, inherent safety principles.
Get it right from the start.
Exactly. Stage 2 is construction. This focuses on quality planning, ensuring materials meet specification, proper fabrication techniques, and that the mechanical completion aligns perfectly with the approved design.
Build it right.
Stage 3 is commissioning. This is where you functionally test the equipment and systems before introducing hydrocarbons. You prove it meets the design specifications and required performance standards safely.
Okay, design, construction, commissioning. Then the ongoing stages.
Stage 4 is operations. This means running the plant strictly within its defined safe operating limits or envelope, not exceeding design pressures, temperatures, flow rates, etc., staying within the lines.
Right.
Stage 5 is modifications. Any changes made during the operational life must, as we just discussed, be rigorously controlled through the management of change MOS process to ensure integrity isn't compromised.
And the final stage.
Stage 6 is decommissioning. This is the planned, safe removal of the installation or parts of it from service at the end of its life, ensuring no residual hazards are left behind. Integrity matters right to the very end.
Okay, so integrity spans the whole life. When are formal inspections actually mandated within that life cycle, particularly during the long operational phase?
Inspections are typically required under three main circumstances by regulations and good practice. First, immediately after installation or a significant reinstallation, to confirm everything is set up correctly and hasn't been damaged during installation, a baseline check.
Makes sense.
Second, and this is ongoing, inspections are required where deterioration of the equipment could potentially cause a significant risk. This is especially true for equipment exposed to harsh environments, offshore platforms, for example, or handling corrosive chemicals or subject to fatigue or extreme weather.
So where things are likely to degrade.
Exactly. And third, inspections are usually required after any exceptional circumstances have occurred. This could include major modifications, known physical damage, like something heavy being dropped on a pipe, or after long periods of disuse where hidden corrosion or seizure might have set in.
All right, check it after something unusual happens. Now, let's discuss the maintenance strategies themselves. Our sources list 7 distinct approaches, which demonstrates that maintenance isn't really a one-size-fits-all problem, is it?
Not at all. The diversity reflects the need to balance safety priorities, operational efficiency, and cost-effectiveness. The strategies range from reactive to highly proactive.
Okay, let's start with the reactive end of the spectrum.
Right. The simplest is emergency or breakdown maintenance. This is basically fixing something only after it has failed. This approach should only be used where that specific failure has absolutely zero safety implications and minimal impact on production. Very limited application in high-hazard industries.
Okay, fix it when it breaks, but only for non-critical stuff.
Then there's opportunity maintenance. This is a bit smarter. It involves performing non-urgent maintenance tasks during a scheduled shutdown that's already happening for another, more critical reason. You're maximizing the use of that existing downtime.
Piggybacking on other work makes sense. And the less invasive repair methods.
You have working adjustments. These are typically minor repairs, tweaks, or tuning activities that can be safely performed while the plant is still running, things like adjusting pump gland packing or minor instrument calibration.
On-the-fly fixes.
Then we have servicing and inspection. This is proactive, but often based on simple checks. It involves routine activities like changing filters, lubricating parts, topping up fluids, or visually inspecting for leaks or wear, looking for early signs of potential failure. And then there's shutdown maintenance, which is planned work that absolutely requires the entire process or a significant section of it to stop because the work on that specific component is critical and simply cannot be done safely while it's live or under pressure.
Right, the big planned turnarounds often involve this.
Exactly. Now, moving to the two most proactive and safety-focused strategies.
Okay.
These are planned preventative maintenance, PPM, and routine condition monitoring. PPM is applied specifically where safety depends critically on the condition of the installation or where equipment is known to be exposed to predictable deterioration cycles.
How does PPM work?
It's typically based on fixed time intervals or running hours. For example, replacing critical seals every 6 months or overhauling a pump every 5,000 hours. Regardless of its apparent visual condition at the time, you're replacing it before it's expected to fail.
Okay, time-based replacement.
Yes. Condition monitoring, on the other hand, is often seen as smarter. It focuses on continuously or regularly assessing the actual condition of safety-critical parts. This uses techniques like vibration analysis on rotating equipment, thermal imaging to detect hotspots, acoustic monitoring for leaks, or oil analysis.
So you're measuring his health directly.
Precisely. It allows for the detection of developing faults and potential failures before a catastrophic breakdown occurs, allowing maintenance to be scheduled exactly when needed rather than just based on time.
That sounds like a much more efficient way to potentially spend resources than just replacing parts every 6 months, if they might still be perfectly fine. This brings us neatly to risk-based maintenance and inspection, often called RBM or RBI. How does this formal process help refine those PPM or condition monitoring schedules?
RBM-RBI essentially takes the guesswork and generalizations out of maintenance planning. It's a formal, systematic process used to rank every critical plant item, pipes, vessels, valves, structures, based on its specific risk profile.
And how is risk defined in this context?
Risk here is typically defined as the product of two factors. The probability or likelihood of that component failing multiplied by the consequence or severity of that failure if it were to occur. You're asking two key questions. How likely is this thing to break? And if it does break, how bad will the outcome be?
Okay, probability times consequence.
Yeah.
Can you give us a practical example of how RBM/RBI might direct maintenance efforts differently for two similar components?
Sure. Imagine you have two identical pipes in terms of material, age, and operating pressure. Pipe A carries relatively harmless chilled water for cooling. Pipe B, right next to it, carries high pressure, highly toxic hydrogen sulfide gas, H2S.
Okay, very different contents.
Right. Now, the probability of failure due to, say, external corrosion might be exactly the same for both pipes based on their condition. However, the consequence of pipe A failing might be a localized water spill and maybe some equipment getting wet inconvenient, but low severity.
Right.
The consequence of pipe B failing, however, could be catastrophic, a major explosion risk, a potentially lethal toxic gas release impacting the workforce and potentially the public. RBM/RBI recognizes this huge difference in consequence.
So what does it dictate?
It dictates that the inspection schedule for Pipe B must be much more frequent, much more stringent, and potentially use more advanced, sensitive inspection techniques compared to Pipe A, even if their basic conditions seem similar. Inspection and maintenance efforts are focused where the risk is highest, ensuring resources achieve the maximum impact in reducing overall plant risk. The ultimate goal is always to reduce risks to ALART as low as reasonably practicable.
Focusing the effort where it matters most. That makes a lot of sense. Before we leave plant maintenance, corrosion seems like a constant, relentless enemy in this industry. What are the main strategies used for long-term corrosion prevention?
Corrosion is indeed a major integrity threat. Prevention generally relies on two main principles, which are sometimes used together. The first and most common is applying a surface coating.
Like painting.
Painting is a form of it, yes. It's about physically insulating the metallic surface from the corrosive environment, whether that's the process fluid inside or the atmosphere outside. This can be done using specialized paints, varnishes, epoxies, rubbers, or even thin metallic films like galvanizing. The key is the integrity of that coating. Any breaches, like scratches or bubbles, become focal points for corrosion and must be repaired.
Okay, barrier protection, what's the second principle?
The second principle focuses on the material itself, using inherently corrosion-resistant materials, CRMs.
Like stainless steel.
Stainless steels are a common example, yes, but it also includes higher-grade materials like various nickel alloys, titanium, or even non-metallics like specialized polymers or composites. These materials possess an inherent resistance to the specific type of corrosive action expected from the product being handled or the external environment.
When would you choose CRMs over just coating?
CRMs are often mandatory, where the corrosive attack is known to be particularly severe, or where mechanical abrasion or high temperatures are likely to quickly damage or degrade any surface coatings, rendering them ineffective. Sometimes, particularly for buried pipelines or offshore structures, organizations also employ cathodic protection.
What's that?
It's an electrochemical technique where a more easily corroded metal, a sacrificial anode, is electrically connected to the structure you want to protect. The sacrificial metal corrodes preferentially, effectively diverting the corrosion attack away from the primary critical structure.
Fascinating. Okay, excellent overview of maintaining the physical plant. Let's move to our final section for this deep dive, Section 5. Controlling specific operational hazards. This seems to focus on specific procedures needed to handle the materials and processes safely during non-routine operations.
That's right. We need to first cover the critical preparatory steps that are often required before any intrusive maintenance work can begin, or even before changing the product handled in a vessel. These are cleaning, purging, and venting operations.
Okay, cleaning, purging, venting. Why are these so essential, especially before anyone might need to enter a vessel for inspection or repair?
Well, before any person enters a confined space like a tank or vessel that previously held hydrocarbons or other hazardous materials, you absolutely must guarantee two things for their safety. First, that no harmful, toxic, or flammable residue remains inside. And second, that the atmosphere inside that vessel is safe to breathe.
Safe to breathe
meaning it contains sufficient oxygen, around 21%, but critically, it contains essentially no flammable hydrocarbons or toxic gases. So cleaning is the first step, physically removing residual liquids, sludges, or solids, often using methods like high-pressure water jetting or steam cleaning.
Get the gunk out.
Exactly. Then you need to deal with the atmosphere. Gas freeing is a general term, often involving blowing large volumes of fresh air through the vessel to displace the hazardous gases. But the gold standard for ensuring a non-flammable atmosphere, especially before hot work might occur inside, is purging.
Okay, how does purging differ from just blowing air through it, venting?
Purging is a much more controlled and effective process for removing flammable vapors. It typically involves pumping a non-flammable inert gas, most commonly nitrogen, N2, into the tank or vessel. This inert gas physically displaces the hydrocarbons and the oxygen.
Pushes them out.
Yes. It pushes them out through vents until the concentration of flammable gas remaining inside is reduced to a very safe low threshold. Typically less than 1% by volume is a common target. This guarantees the vessel atmosphere is gas-free in terms of flammability. After purging, you would then typically need to ventilate with air to ensure sufficient oxygen for breathing before entry is permitted.
Got it. Purge with inert gas, first for flammability, then ventilate with air for breathing. And then there's another related term here, inerting. How is that different? Is it used for vessel entry?
Inerting isn't usually for vessel entry. It's more about actively maintaining a safe, non-flammable atmosphere, often during storage or certain operational phases. It involves deliberately creating and maintaining an atmosphere inside a tank or system where hydrocarbons simply cannot burn.
How do you do that?
By introducing and maintaining a high concentration of an inert gas again, usually nitrogen, but sometimes carbon dioxide, CO2, or even steam can be used. The goal is twofold. First, it increases the lower flammable limit, LFL, of any remaining hydrocarbon vapor, meaning it takes a much higher concentration of fuel vapor to potentially ignite. And second, and more importantly, it drastically reduces the oxygen concentration, typically well below the level needed to support combustion, often below 5–8% oxygen.
You're removing the oxygen leg of the fire triangle.
Precisely. Inerting is commonly used, for example, to maintain a safe nitrogen blanket above the liquid level of a flammable product in a storage tank, preventing air oxygen from mixing with the vapors in the headspace. Or it might be used to keep an empty tank safe by filling it with nitrogen, preventing any potential ignition of residual vapors.
Okay, makes sense. Now, controlling ignition sources during maintenance is obviously paramount. What are the most common fire hazards that maintenance activities themselves can introduce into an already potentially volatile environment?
The hazards are numerous and sometimes subtle. The most obvious one we've mentioned is hot work welding, cutting, grinding, anything that intentionally generates heat, sparks, or open flames. That's a primary ignition source.
Right. What else?
Other common ones include the unsafe use or storage of flammable materials brought in for the maintenance task itself, things like cleaning solvents, paints, temporary fuel supplies. Also, faulty electrical equipment is a major risk, particularly defective portable hand tools, extension cords, or temporary lighting. Their sparks can easily ignite flammable atmospheres.
Even simple things.
Even simple things. Workers smoking in non-designated or unsafe areas is a classic ignition source. Even using non-intrinsically safe portable electronic devices like phones or radios in hazardous areas, or using defective temporary space heaters in workshops or temporary habitats.
So given these diverse ignition sources, what are the mandatory precautions necessary to control them effectively?
Again, procedural rigor is the main defense. For hot work, the strict use of the hot work permit system is essential. These permits mandate specific precautions like clearing combustibles, having fire extinguishers, and maybe charged hoses ready, and often require regular fire safety checks during the work. And for a defined period after the work stops, this is known as a fire watch.
Keep watching even after the sparks stop.
Absolutely. Smoldering can take time to ignite. All welding, burning, and other hot work must only be performed by competent, qualified, and authorized persons. Organizations should also actively consider if the work can be done differently. For example, could components be fabricated off-site in a safe workshop environment and then brought in, minimizing hot work on the live plant?
Design out the risk where possible.
Yes. Furthermore, all portable electrical equipment used must be subject to regular inspection and testing, often called portable appliance testing, or PEAT testing, to ensure its electrical safety and integrity. And, of course, strict control over the storage, handling, and use of all flammable liquids and gases is paramount, along with clear rules and enforcement prohibiting smoking or other ignition sources in hazardous areas.
Okay. Now, I find this next point fascinating. The challenge posed by something seemingly innocuous, water. The outline mentions it as a triple threat in these specialized hydrocarbon processing environments. So what does this all mean? How can simple H2O be such a problem?
Water is deceptively dangerous in hydrocarbon facilities for several key reasons. First, the flashing hazard. If liquid water is inadvertently introduced into process systems or vessels operating at temperatures above its boiling point, 100 degrees Celsius or 212 Fahrenheit, it will instantly and violently flash into steam,
creating huge expansion.
massive volume expansion, generating immense pressure very rapidly. This can easily exceed the design pressure of vessels or piping, leading to catastrophic rupture. It's a major hazard during startups if water hasn't been properly drained.
Okay, that's threat number one. What's the second?
Second, water can react, sometimes violently, with certain process chemicals. For example, it can react with some acids, catalysts, or reactive intermediates, potentially causing runaway reactions, generating toxic gases, or producing unexpected heat.
Chemical incompatibility.
Yes. And third, on a longer-term scale, water is the primary driver for internal and external corrosion of carbon steel equipment, which is the most common material of construction. Even small amounts of water accumulating in low points can lead to significant metal loss over time, eating away at the acid integrity we discussed earlier and eventually causing leaks or failures. So, flashing, reactivity, and corrosion, that's the triple threat.
Right. And then there's a specific water-related issue mentioned, hydrates. These sound like solid ice-like formations. These are a real operational nightmare, aren't they?
Oh, they are a massive operational headache, particularly in natural gas production and transportation systems, especially in colder climates or deep water. Hydrates are solid, crystalline, ice-like compounds that form when natural gas containing even small amounts of water vapor is subjected to low temperatures and high pressures conditions common in pipelines and processing equipment.
So they're not just ice.
No, they're clathrates water molecules forming a cage-like structure that traps gas molecules like methane inside. They look like ice or packed snow, but they can form well above the normal freezing point of water, sometimes even at 15-20 degrees Celsius if the pressure is high enough.
And what problems do they cause?
They rapidly accumulate inside pipelines, valves, and instrumentation, acting like cholesterol in an artery. They cause severe blockages that restrict or completely stop the flow of gas.
Which causes pressure buildup.
Exactly. This leads to significant production losses, and more dangerously, the blockage can cause excessive pressure to build up upstream, potentially leading to pipeline rupture if not detected and managed quickly. Dealing with hydrate plugs often requires shutting down the system, carefully depressurizing it, and then using methods like heating or injecting chemicals like methanol to melt or dissolve the plug, a costly and time-consuming process.
A real showstopper then.
Oh.
Okay, finally, let's detail the absolute final checks required before restarting or recommissioning a piece of equipment or a plant section after maintenance has been completed. These post-maintenance checks sound critical to avoid startup incidents, which are unfortunately quite common.
They are absolutely critical. This is the moment where the operational team confirms that the patient is ready to come off the operating table safely and that all the temporary safety measures put in place for the maintenance team have been properly and completely removed.
What temporary measures are we talking about?
Well, remember, prior to the maintenance starting, all relevant energy sources and process fluids were stopped and isolated. Systems were likely drained down. And crucially, for positive isolation, physical blanks were probably inserted into the pipework.
Remind us what blanks are again.
Blanks, sometimes called spades or spectacle blinds, are solid metal discs that are physically inserted between pipe flanges. They provide a robust, positive physical barrier to ensure absolutely zero possibility of hazardous product leaking or flowing into the section where people are working. They're much more secure than just relying on closed valves.
Okay, a solid steel barrier.
Yes. So the post-maintenance check must rigorously establish that all the isolations have been correctly remade, meaning valves that were closed are now reopened correctly, LOTO devices, locks and tags, have been properly removed by the authorized personnel,
Right.
and critically, that all temporary blanks, spades, hoses, tools, and any other service equipment used during the maintenance have been physically removed from the system before startup is attempted.
Why is confirming blank removal so critical? What happens if one gets left in by mistake?
Leaving a blank in place inadvertently is a classic high-consequence failure mode during restarts. If a blank is left in a line that's supposed to have flow, it will completely block that flow. When the system is pressurized or pumps are started, pressure will build up rapidly behind that forgotten blank, potentially leading to overpressure and catastrophic rupture of the pipe or equipment. It happens more often than you'd think.
Wow. Okay, so meticulous checking for removed blanks is vital. What about integrity testing after the work?
Yes, depending on the nature of the maintenance, further testing is usually required before full recommissioning. This includes functional testing of key safety items that might have been disturbed, things like pressure relief valves, PRVs, or bursting discs need to be confirmed operational and set correctly.
Make sure the safety valves work.
Exactly. The system often requires pressurization checks, usually with an inert gas like nitrogen first, to check for leaks at any disturbed joints or flanges. This might be followed by a formal pressure test, sometimes hydrostatic with water or pneumatic with gas, to prove the mechanical integrity of the system, especially if major components were replaced or repaired.
And what about new welds?
For any new critical welds made on pipework or vessels during the maintenance, non-destructive testing, NDT, is mandatory. This uses techniques like X-ray radiography or ultrasonic testing to examine the internal quality and integrity of those welds without damaging them, ensuring they are sound before the system is put back into hazardous service.
Okay, final quality check on the repair itself. This entire Element 2 framework we've walked through. Contractors, PTW, ILOTO, handover, MOSI, asset integrity, maintenance, operational controls. It really synthesizes everything, doesn't it? It's a massive, interconnected, comprehensive system designed to manage risk.
It really is. You see how procedural rigor, things like the permit to work system, the management of change process, effective handover communication, is constantly interacting with and supporting the physical integrity of the plant, which is managed through things like the asset integrity management systems, risk-based inspection, and corrosion prevention.
They work hand in hand.
They absolutely have to. The core takeaway, I think, for you, the learner, is that safety in this high-hazard industry isn't just an add-on or an optional extra. It is a daily, minute-by-minute commitment to procedural detail and discipline. These procedures aren't just bureaucracy. They are designed deliberately to impose that discipline and ensure that competence and comprehensive, verifiable documentation act as the ultimate necessary barriers against catastrophic failure.
That's a powerful summary. We've seen today how something like safe isolation requires a complex multi-step sequence. ULTO, warning notices, discharging stored energy that has to be executed perfectly, often under time pressure by human operators.
Wow.
This brings us to a final provocative thought for you to consider. If the safety of a multi-billion-dollar installation and the lives working on it is so heavily dependent on the successful, error-free execution of multiple complex sequence steps by human beings, how can organizations genuinely ensure consistently high reliability during those inevitable moments of high stress, fatigue, or urgency? Moments where the temptation to short-circuit those procedures, maybe skip fully discharging the residual energy to save time, or fudge a signature on a permit might be greatest. What systems, or maybe what kind of culture, can fundamentally defend against that innate human desire for a shortcut when the pressure is on?
That's the million-dollar question, isn't it? Maintaining that procedural discipline, especially when things get tough, requires more than just rules. It requires leadership commitment, constant reinforcement, and ultimately, a deep-seated organizational culture that genuinely values following the procedure over taking the shortcut every single time. Definitely something to consider as you reflect on this entire framework.